So here we have a problem asking us to find the electric field outside and inside of a cylinder, and as you can see, the cylinder is uniformly charged with a radius r and a charge density lambda. So the first part, you're looking for the electric field outside the cylinder. But before we do any of that, first we need to draw a diagram, which I did. And you can see I drew the actual cylinder, and then the two Gaussian surfaces, the one inside and the one outside. And then I parameterized the length and the charge density and the radius and all that good stuff. And then I chose a Gaussian surface, which was a cylinder, because that means that my angle between the normal and the electric field is 0, and if it's 0, then the dot product of E and ds is just EDS. And since that angle is constant, that means that E is constant, so you can take it out of the integral, and also, by the way, this is Gauss's law, so we're using Gauss's law to find the electric field. And so, like I said, electric field comes out because it's a constant, and then this closed double integral of ds is the surface area, in this case of the cylinder, which is 2 pi RL. And then, so that's the left side, and then on the right side you have charge enclosed over epsilon naught, and charge enclosed is defined as the charge density times the length, because charge density is charge per length, and if you multiply that by length, then you get charge, which is the charge enclosed. And so you substitute in lambda L for charge enclosed, and then you solve for E, and then you get the magnitude of the electric field when it is outside of the cylinder. So yay, that's part A. And then for part B, you do the same thing. You use Gauss's law. The only difference is that you use a 3D charge distribution instead of the 2D charge distribution. And the reason for this is because is to differentiate between this equation and this equation. And so because of that, your charge enclosed is equal to rho times the volume, which is pi r squared times L. And then in order to relate this equation to the previous one, you want to write rho in terms of lambda, and lambda times distance, or lambda times the length equals rho times v, and then you solve for rho and you get that, and then you substitute that in and do your algebra, and then you get this equation for the magnitude of the electric field. And then once you have that, you compare it to the other one by saying r is equal to r, or little r is equal to big R. And when you substitute big R for little r in this equation, you end up getting the other equation. So that tells you that when little r is equal to r, that the electric field is the same. And that's it. Alright, thanks.